Hello everyone. Today we're going to present our research on the deep reinforcement learning for adaptive traffic signal control. We are group 18 and our research is mostly based on the reference in the below. Today we'll cover the four aspects. Firstly, the introduction, then the methodology, third, the experiment, and then the conclusion. Well, firstly, I'll give you a brief introduction on the background and the significance of our study. Well, the traffic congestion is a prime concern in the traffic management and causes much economic loss to both the government and our individuals. A previous study revealed that each driver in the United States paid over $1,000 and approximately 100 hours for congestion annually. And for today, the most efficient way to deal with the traffic congestion is to implement the traffic signal control. And there are mainly three categories of the traffic signal control. The first one is the fixed time control, and then the vehicle actuated control, and then finally the adaptive signal control. However, the first two methods has the shortcomings of it is insensitive to the dynamic traffic demands and it fails to react to sudden accident. And the third method, adaptive signal control, could overcome those shortcomings. It is more flexible to the stochastic traffic demands and it could distribute the green time more efficiently. Well, there are some, the reinforcement learning is widely used in the adaptive signal control, and it has the advantage of successive self-management and self-optimization. And it is also good that it could be exempt from prior knowledge. Well, however, it is based on human craft features such as the queue length and average delay. Those are the problems with reinforcement learning because the human crafted features cannot cover the whole pictures of our traffic conditions. To deal with that, we could use the deep reinforcement learning to extract the features automatically. Well, however, there are still some problems with the deep RL because it is often induced instability and divergence while learning. Well, there is one solution that could implement to overcome those shortcomings that is to implement the experiments, reply, and the target network.
The problem is described as an intersection with four roads shown on the left side. Each road has four lanes of traffic in different directions. At this intersection, vehicles operate under the control of traffic signals. The state includes three elements, which are speed, position of all vehicles in their intersection, and the traffic signal choice. For each road, we divide the lane of length L into several cells of length C, as shown on the right side. The position and speed information of each vehicle are recorded into corresponding cells. The position information is represented by the binary variable where 0 represents no vehicle and 1 represents one vehicle there. And the speed information comes from the Rhythm software. Thus, we denote the position information in each road by 4x(n) matrix T, similarly for the speed matrix V. Moreover, we use a vector L to represent the state of the signal. It has four choices since the agent can only choose between four action combinations. For example, turn on the green lights for south to north road with the first element set to be 1. Detailed representation can be seen in the report. And four phases are predefined as depicted here, as the action space consists of two elements here, 0 and 1, representing continue for the green light action with AT equals 0, or switch to the next phase with AT equals 1. An intergreen interval is included if the action between two consecutive time steps are distinct. And this page gives an example of signal timing plan. To start with, a fixed green light duration tau g is given for the first phase, and the agent shall execute one action after observing intersection state st at the beginning of each time step t, as illustrated here. The new time step t plus 1 starts at the end of the current green interval, after which a new intersection state st plus 1 is observed, and thus new action t plus 1 should be determined. The green intergreen period consists of two elements, a yellow light with duration tau y and an all red period with duration tau ar. The traffic signal timing point corresponding to the action is shown on the right side. Note that the same action can be chosen consecutively. And for the reward mechanism, it's designed to evaluate the vehicle's total waiting time resulting from each action at the intersection at each time step. As depicted here, two observations will be conducted for every time step. The first observation occurs at the start of the green light period, and the second observation occurs at the end of the green light interval. They collaboratively capture the characteristics of the vehicle's total waiting time at the intersection at each time step. To obtain the total vehicle waiting time, two new variables Wt and Wt prime are determined accordingly, defining the reward as the difference between two total waiting times observed at two different timestamps as shown here. And finally, the key learning process aims to maximize the reward of an agent by taking a series of actions in response to a dynamic environment. Since the agent's long-term goal is to minimize vehicles' dwell time, the agent should evaluate the interpretation of current policies on the future and the weight of consequences and develop an action strategy pi. And eventually, the agent should follow some algorithm to find an optimal policy pi star giving maximum Q value.
We use the deep neural network to replace the Q table of the Q-learning algorithm. In our DNN network, the input of the network is observed state, which is denoted by ST. It contains three kinds of the information: the speed information, the position information, as well as the signal state. And the output of the network is estimated Q table values with the parameter theta for all actions. We first feed the position information matrix into the state subnetwork, in which the first layer is a convolution layer. It convolves the position information matrix with 16 filters of 4 times 4 with 2 strides, followed by a nonlinear activation layer ReLU. The second layer is also a convolution layer, which convolves the result of the first layer with 32 filters of 2 by 2 with 1 stride, followed by another nonlinear activation layer ReLU. We then feed the speed information matrix into another state subnetwork, which share the same structure with that of the position information, but they have different parameters. Finally, we incorporate the signal state with the flattened outputs of the two subnetworks, which is the input of our third layers as shown in the above figure. The third and fourth layers are both fully connected layers, which have 128 and 64 units respectively, followed by another nonlinear activation functions ReLU. The final output layer is a fully connected linear layer, and it outputs the Q value of state action pairs for all possible actions. Then we train our DNN network. In the training process, the input of training data is a set of state action pair, which can be retrieved from replay memory M, and the output is a set of the Q table of state action pair. Agent records interaction between the environment and its decision of each time step into a replay memory M. To reduce the computation cost, we use a stochastic gradient descent method. We adopt the RMS prop with mini batch of size 32 in estimation. We ask the agent to train the network with random choosing 32 samples from the replay memory. We hope to estimate the parameter theta such that the output Q value can best approximate the target Q value. However, the target Q value based on the parameter theta prime is unknown. Thus, we propose an estimated method to obtain the target Q value by RT plus gamma times max Q value of the next state for all actions. We update theta prime with the DNN network parameter theta every 3 steps, and it holds a fixed between the individual updates. Hence, with the training data, we estimate the optimal parameters by minimizing the mean square error, which called the MSE, which is given on the slides, where n is the size of the data, RT is the reward of the current decision of the current reward of the time step t, gamma is the discount factor, and A prime is the set of the all possible actions.
In the experiment, we use a popular microscopic traffic simulator VISM to simulate traffic operations. With the aid of a common interface in VISM, it is very convenient to set traffic arrivals, obtain traffic states, and control the signals. It is a very good platform for implementing the DRL for traffic signal control. Layout of 4 signalized intersection is like this, and the length of the approach is about 200 meters, and the sail length is about 7 meters. And then some maximum speed, traffic demand yellow interval or red interval are set. For the hyperparameters of DQN, discount factor, epsilon, learning rate, memory size, bench size, and other parameters are all set properly for obtaining a good optimal policy. Then the classical Webster's model with phase clearance reliability is adopted as a benchmark, also called the baseline. This method is from the IEEE paper, and the PCR is defined as a probability that the traffic arrivals can be cleaned within the green time of the phase. In the results, the average vehicle delay obtained from the VISM is used to evaluate the performance of DQN and the baseline. And the performance of the proposed DQN model converges over time, and it learned a good action policy for control. And our model performs significantly better than the baseline by reducing the average vehicle delay by 34%. This is the video about the training process, and we use the spider to code the DQN and control the VISM. Then the signals is controlled, and we can say that the vehicles are all pass through the intersections, and the green time didn't waste. In conclusion, this paper proposes a deep reinforcement learning algorithm DQN for dynamically controlling the traffic signals. The agent can automatically select valuable and important characteristics of traffic conditions for training, and our algorithm performs better than the baseline. For the future direction, a real-world deployment is required for TSA to demonstrate the applicability of deep RL-based control. And due to the disparities between simulation and the reality, transferring control rules acquired in simulation to reality continues to be a problem. That's all. Thank you for your listening.